In fact, this talk is going to be probably a bit shorter than typical, and to compensate on that, I have two talks in one. So if I find out that it's too short, I start the second. Okay. So let me dive in directly to the model. I'll make some more general comments a little bit later. But for the moment, let's just introduce some notation. So we are working on the torus. Discretized at step epsilon. M is going to be a mass which takes care of long time behavior. And then there's a GFF law on that torus with a mass. So for aficionados of random walks, it just means you run the random walk with killing that is related to M, so everything is well defined as long as M is positive. Okay? And you have a covariance on that discrete set. Of course, the variance at a point, so the covariance is just C infinity, but the covariance of the Gaussian field that you get here, it's a green function of that random walk killed M square, and then you have the variance, which is of order log 1 over epsilon. Okay, so that's a usual discrete. So discrete can mean two things. Here, when I say discrete GFF, I don't mean the values are discrete. I mean really a Gaussian vector, but indexed by the discrete set, which is the epsilon lattice. And since it is not the focus of the first talk, I'm not going to discuss M at all. It's just there in the background. You can think of M equal 1, and I'm not going to refer to it, and therefore I'm going to omit it from most of the notation, at least when I remember to omit it. So sometimes it may pop up and down, but just disregard M. Now, what is the Liouville measure? The Liouville measure is very simple. You introduce the total mass of the multiplicative chaos with parameter beta associated with this Gaussian field. So you take the exponential. Integrals mean really sums, but I find it convenient to write integrals. So it's sum normalized with volume elements. So if you plug in here 1, you will get, instead of this whole beast, you will get just 1. And this fancy weak ordering is nothing in this context by the usual rescaling we put in order to get a Gaussian multiplicative chaos. Okay? So what is written here is the GFF weighted by the negative moments, negative exponential moments of the total mass of the GMC associated with the field.
So you said it, but here the mass is not rescaling with epsilon.
No, but the thing is exactly this delta epsilon. The delta epsilon is rescaled. So the mass is mass really of volume 1, which makes sure that the variance remains log 1 over epsilon plus a constant that depends on the mass. Okay? So, yes, the conventions about rescaling in this business are probably the most confusing and most complicated of the whole business. Okay, so I'll keep this weak notation, although for people who come from a different part of the woods like me, it's, I think of it really as a rescaling that makes sure that this object has mean 1. Okay. Now, note, you can think of it as a measure, as a weighting of the Gaussian measure by some potential which depends on your field. So this V0 epsilon is some potential that depends on your field. And note that this potential is a pointwise potential. So it's not a gradient type. There's a whole different class of models in which the potential has to do with gradients of the field. That is not the case here. Okay, so now, sorry, just simple reparameterization that makes it into constants that don't have pi and floating around and stuff like that. So there are two parameters, b and kappa. B runs between 0 and 1 in the range that we care about. I should have mentioned that, of course, we are interested in limits as epsilon goes to 0, and therefore we'd better have that this integral does not go to 0, or does not, that no bad things really happen, and for that you cannot take beta too large. So the full L1 region corresponds to B between 0 and 1, and kappa is a parameter that will show up in just a second. So the main theorem that I want to discuss is that the law converges weakly if you rescale, if you think of the field as a distribution over test functions. So it converges weakly so the field converges weakly to a limiting phi LV, which is a distribution valued. So that's the first part of the statement. But maybe more important for question of perspective, but maybe more surprising, is that the field can be coupled with the GFF in such a way that A, the difference is always negative, so you're always below the GFF values. And second, the difference field is very regular. So it's Holder continuous with a Holder exponent, at least as good as what I wrote here. The two authors have a discussion whether this is optimal or not. And I will not tell you who thinks what, but I can just say that there is confusion about the question whether this is optimal or not, whether to expect it to be. We definitely don't prove that it's optimal, but whether or not to expect this weird change from Lipschitz to Holder at the particular value, that's what we get. So everything is on the torus, but there's a mass. Okay. A corollary of this statement is that we can discuss extremes. Yes, please.
Are those the exponents in the Cameron-Martin space of the...
Sorry?
Are those corrections in the Cameron-Martin space of the GFF, so that at least it's consistent with absolute continuity?
I would guess yes, but I'm not. It's certainly as a distribution, it's absolutely continuous, but I mean, once you couple, it's absolutely continuous as a distribution, or as a measure. But good question. I don't know.
Can you repeat the question?
Sorry?
Can you repeat the question?
The question was whether these functions are in the Cameron-Martin space. Functions with this regularity. I think the answer is yes, but I don't want to commit myself.
Kappa equal 1 why is special kappa equal 1? It does not.
I don't know. That's what we get. So that's part of the discussion between.
Special value for B, right?
So
This one B for kappa equal.
no, B01 is the full range, the full L1 range.
It's not a boundary of the domain for B.
No, it's not the L2 phase. It's what comes from the proof. It might very well be that the proof is not optimal. So I would not, at this point, I would not put any. Maybe I will explain a little bit when we get to it what happens. What is the important thing is that the regularity, or at least the way we approach it, the regularity is worse near high points of the field. And so they are determining the regularity, and we don't control there very well the correlation between the modulus of continuity and the value. So it might be, we're using at some point Cauchy-Schwarz or something. It might very well be that this is not optimal.
What is lambda?
Sorry? Lambda is just where is lambda?
The definition, in what ways the Liouville,
So there was a tilt here. Yeah. Yeah. So, okay. Lambda? Okay. Good. So that's the result. So what about extremes? Well, the statement is the following. Take m epsilon, which is this quantity. GFF people will recognize it as the right centering for the maximum for the 2D. So in particular, the expectation of the maximum of GFF is exactly m epsilon plus order 1, not just the expectation. In fact, the maximum itself of GFF is a random variable which is tight around an epsilon and has limit laws, whatnot. And the theorem is using that coupling that was constructed before. One can show that the maximum of the Liouville field minus the same centering converges to what it should converge. So there is a Gumbel random variable, there is an extra, not positive, log of a positive random variable, which is independent of that Gumbel, and then there is some other constant, and everything here depends on M. I want to emphasize that. So I'm not discussing the dependence in M. In fact, it will show up in the open problems later. Okay? So, are there questions about the statement? The statement is what you would expect. If everything were Gaussian, this is what you would get. So if lambda were 0, this is what you would get. Okay. So,
Are you going to explain how to obtain this corollary from the first result?
okay, yes. So I was not going to explain, but let me explain now. I was going to say that this is a well-paved road that we are just following. And what is this well-paved road? You will see that we will construct the difference between the GFF, the GFF and the Liouville fields. We will construct it recursively, in a sense, as function of the scales of the noise. We will go from rough scales to fine scales of the Gaussian, and this will construct recursively a sequence of approximations of this phi delta. And this sequence of approximation converges. Okay, that will be the main theorem, and this is what you need for the coupling. Once you know it converges, it means that it's essentially measurable on, it converges in soup nodes. That's the important thing. So it means that it's essentially measurable on the coarse field of the GFF. It has nothing to do with the fine field. And now you can understand why you get the result, because the usual result tells you you have a coarse field that determines the derivative martingale whatnot. This difference is modifying it. So you get a new coarse field, which is actually Holder continuous with that regularity, whatever. And then you continue essentially with no perturbation anymore. Okay? So once you continue with no perturbation, you're going to get Gumbel.
so that should also give you this ZLV, right? Because you just get an exponential weight.
The problem is, yes, it gives you the ZLV. So this ZLV is going to be the derivative martingale, the usual Gaussian, plus a random variable, but that random variable is dependent on it. So to establish the exact dependence, yeah, it's a solution of an SDE. You can write some expression, but it's not very explicit.
It's not a log of the Liouville measure integrated against the exponential of the difference.
I don't think so, but I don't know. Okay. We have not made a big effort to identify this extra change. We just prove it converges. And in fact, there's an equation for it, which is driven by the coarse field. So in principle, you could try to analyze it. We did.
Because I know that this is, well, at least, you know, the way I looked at it, true about the previous work on this in the context of the, there's like the sine
Gordon. We'll get to mention
where I think this is true.
That might very well be true. That might very well be true. Here it has a definitive sign. So I don't know, but it might very well.
Your correction also has a definitive sign.
Sorry?
Your correction has a
My
definitive.
correction,
Right, exactly.
which is not true for sine law.
Right.
Okay. So let me, so the approach, as I said, it's a well-paved road by now, even though the paving was not so long ago. So we follow this approach of the Polchinski equation, which comes from the physics literature, but which has really, in this context, been developed by Roland Bauer-Schmidt and co-workers, among them Michael. There's a very nice archive review. So for those of you who hear for the first time about Polchinski evolution, there's a very nice pedagogical review that explains what exactly is going on, and I'm going to summarize this review in 2 slides, basically. I just want to mention that the same review makes the point that if you come from other parts of the wood, this is very closely related to Eldon's stochastic localization, which has come from high-dimensional probability and has had some very significant successes in that field, including the resolution of the slicing conjecture, all sorts of things in high-dimensional probability. And the idea in both cases is you want to construct a complicated measure, and you don't know how to do it, or you want to understand the complicated measure. So what you are going to do is you start from a very simple measure. For example, in the context of Dan's work, this would be, I don't know, a Ising model or a spin glass model or something like that. So you start from a simple model, say a Dirac at 0, and you start evolving it in a way that is guaranteed to bring you to the measure you care about. So how does it work? So basically, 1/6 a measure. So nu0 is a measure that we want to get to. So we want to write nu0s of f as a composition of 2 things: a floor on f, and, if you wish, a Radon-Nikodym derivative that is replacing f by something else, and an outside measure, nu t. Now, it looks as if I start from t, but in this business, people are used to starting from infinity. So, if you want to end up at 0, at nu0, if you start at infinity in some stupid measure. So what is a stupid measure here? Well, the stupid measure here is just a Dirac at 0. So at infinity, your new infinity is a Dirac at 0. So, of course, P0 of f should be just f, should be the identity map, right? Because if you substitute here t equals 0, pt had better be just the identity map. On the other hand, if you start at infinity, then nu infinity is a Dirac. So then P infinity should involve what nu0 is, which is just if you put here phi equals 0, you recognize, mu is your Gaussian measure, and you recognize the weight you had e to the minus v0 with a normalization constant. Okay? So the two extremes are kind of clear, and it's not at all clear why doing such a crazy thing is useful. Let me emphasize, by the way, that in this writing there is nothing Gaussian. This is, in principle, an approach that you could try to do and invent your own favorite flow and your own favorite sequence of measures. And indeed, for different applications, you might want to do that and not use what I'm going to talk about. In the Gaussian case, there is a natural decomposition, which is related to the question that one has asked before, which is we can decompose the covariance, Ct, right? What is a green function? It's the integral of the transition density. So we have a pointwise CT dot, which is just the heat kernel at time t. And C infinity is just, the green function is just the integral from 0 to infinity of that heat kernel. So we have a very natural scale decomposition as function of t, which also correspond to a scale decomposition in terms of the Gaussian, underlying Gaussian field. Okay, the scale decomposition would be exact if you thought of the heat, and it's a good mental picture if you think of the heat kernel as being an indicator on a ball of radius square root t. If you do that, then it's kind of clear what is going on. Okay, so as I said, CT dot is just the heat kernel at time t. You integrate it between 0 and t. That gives you the covariance. And now you introduce the following objects. So one is the renormalized potential. So the renormalized potential has two parts, right? So the potential is a function of phi. Here we are on an epsilon lattice, so there is no discussion about which function space are we living in, etc. It's just a big vector. So Vt of phi is just a function of your vector phi, and it's obtained by smoothing out phi plus a field where the field has covariance Ct epsilon. So this Ct epsilon is on zeta. Okay? So you're kind of smoothing the fine scales. So the renormalized potential is kind of taking the original potential. You think of phi as something that lives at all it comes from coarse scales up to t, and you add to it a fine field, this zeta, and you average over the fine field. And then there's a flow, which you can define in terms of this formula. And the important thing is that the flow involves smoothing over the scales between T and S. And in fact, you can write okay, I call it PD because people call it PD because they're used to think of in the continuum. Of course, in the discrete setting that I'm talking about here, this is really a vector OD, right? With a long vector of coupled ODE, vectorial ODE, for Vt, which I will save you from. I've not displayed because it would require introducing notation, etc. But what is important is that this leads to an actual, you can use that. So first of all, it's not obvious, but you can verify that with the definitions I gave here, the basic relation I wrote is satisfied. So your measure nu0 of f is equal to nu t of p ptf. And pt is p0t. So it's really involving this smoothing we talked about. And in fact, you get a stochastic differential equation for the field. Of course, the stochastic differential equation has a drift which depends on this renormalized potential. So it's not as if you have something super explicit, but because of Vt, remember, the renormalized potential, you have to take the expectation. Sure, it's a Gaussian expectation, but it's not necessarily very simple to evaluate. Okay. But what comes out from this formula is that you can write the difference field as just an integral from t to infinity of this expression. Okay, because if you didn't have a potential, the integral of the Brownian part is exactly the GFF thing at time t. Okay? So this gives you directly a coupling. This is a coupling. It gives you a coupling between the Liouville field and the GFF field, which is given like. Question?
Is it sure that you need the mass to implement this? Because
Well, I need the mass to start with to make sense of V0. If you don't have mass, you're on the torus, the walk lives forever, the pointwise variance is infinity. You have to truncate at large times. Of course, you don't have to put mass, you could just do the integration up to a finite time. Mass is kind of a way of doing it in a smooth way. But you could stop at some capital T, which is independent of epsilon, it would have the same effect. But otherwise, the object is not well defined.
Maybe on the question, do you need a torus? You could just walk.
No. So, yeah, so all of this generalization they probably are not that important, but I want to emphasize one thing that is important, which is always going to be, you need this object, this C dot, we will need it to be positive entry-wise. So a hit kernel is very nice for that, but other objects might not be. Okay, yes?
I have a more nice question. The W.
It's a vector of Brownian motions, right? It's indexed by x. So this is a vector equation. There's an index x. X belongs to omega epsilon, to my discrete lattice of size epsilon. And the Brownian...
So if one removes the potential, why would we have?
Because you would get here something which has covariance, the integral of Ct dot. The integral of Ct dot is exactly your covariance, right? Okay, so this is y to the power 1/2. And the power 1/2 is not pointwise. Let's be clear about that. It's a matrix, right? Ct is a matrix. It's a matrix to the power 1/2. And therefore, the covariance is going to be this times, it's a symmetric matrix, so it's going to be this guy square, which is going to be Ct dot, and when you integrate, you get the full covariance. Okay? Yes?
Can you remove the mass involved with boundary condition?
Can you remove?
The mass involved with boundary condition?
Yes, but then you lose some homogeneity, and we have not done it, but yes, probably you could do that as well. Yes?
Just to clarify, the SDE runs in the positive direction of time or in the negative?
Well, it's written here in the positive direction. It's an SDE, but you should really think of it reverse time. That's the most confusing thing here. You should think of it going from infinity.
But it's Ito going in the positive direction of time somehow.
It's Ito going in the positive direction of time. It doesn't really matter Ito or not because this is deterministic. So there's no issue of Ito. Right? The stochastic integral has a deterministic integrand. So there is no Ito, Antonovich, whatever correction because it's a deterministic integrand. Okay? The variance does not depend on the field. If it were, it would, then your questions would be pertinent and delicate. But in this setup, it's not. Okay, so you can understand this equation without knowing anything about Ito. You just need to know something about Gaussian processes. That's all you need for this equation. Okay? As soon as you control this object, the drift, you're fine. And what we are going to show is that this drift is bounded and in fact very nice. Okay, and since you were asking the question, it does take a little bit of care, mostly because it sounds a bit silly. There's an issue at infinity, which is, of course, at infinity nothing should happen, nothing should be going on because there is killing, there's a mass that kills you at infinity, so infinity should not affect. But the things are slightly more delicate than that, so you have to do a little bit of massaging at infinity. If you did what, I don't remember whom suggested here, not to take mass but to take finite time, then all this massaging at infinity will disappear. Okay. So So what do we want to do? Eventually, we want to do two things. First of all, we want to take t to 0 for a fixed epsilon and to control this integral. And second, we want to take epsilon to 0 in order to get a continuous limit. Okay? I will focus on the first step. All estimates are going to turn out to be good and uniform in epsilon, and therefore the second step is just routine. So the main issue is to control the fixed epsilon, to get good controls that don't blow up on you with epsilon. Yes?
Is the integral going to be positive because of your coupling statement? So you said that the coupling is such that the Liouville field is strictly smaller than the GFF?
Yes.
And so that will be reflected in the fact that the integral is going to be strictly positive, or?
Yes, yes, absolutely. That's exactly, so C dot is positive entry, and we will see that the gradient is positive. Or positive or negative, I mean, in the right, with the right sign. Okay. So now comes the simplification. So I'm talking about Liouville. In principle, everything I told you, you could do for your favorite potential. But then it's your job to say something about the resulting object. So here, this Vt epsilon is minus the log of this expectation. I've just copied it. So if you take the derivative, so you're thinking of it as a vector, right? It's a function of a vector. So this is the derivative with respect to the x-coordinate of the vector, and forget about the epsilon square normalization, which might confuse you. So just think of it as if it were continuous. Then you get just this object. You just take the derivative with respect to phi x. Okay? And that's what you are going to get. And now comes the following thing. Because zeta has positive correlations, you can bound this expectation of product of two increasing functions by the product of the expectations. Here the Liouville is very important, the fact that your potential is monotone. And therefore, once you do that, and you use the differential equation that we talked about, you end up with, trust me, I've not done anything except to write it explicitly, you end up with an expression which looks like that, okay? So you have the exponential of phi. And we used here the gradient bound. And now you have here phi.
What is LS?
Yes, it should have been written. LS is log of 1 over S. With an M factors and kills things when S is
That
large.
comes from the bound of the derivative. Did it show up?
Yeah, it comes from the weak ordering, right?
Okay.
All this is coming.
I see, okay.
Yes, so this is what you get. Now comes the second step. So remember, one-sided bound we had for free. This is just by monotonicity properties, by the positivity of all sorts of things. The second side, well, since we know that the phi leaf is smaller than the GFF, we can replace the Liouville field by the GFF field to get an upper bound. And that's fantastic because GFF fields we know a lot. A priori on the Liouville field we don't know much, but on the GFF we know a lot. And in particular we can be really rough and replace the GFF field by its maximum. Okay? Of course we lose. At this step we lose. Because you have replaced a field that is very rarely high by something that is high everywhere. But it turns out, and here is the effect of killing, which tells you that this integral is really on a finite interval. I mean, infinity is not causing any issue here. Okay, once we are in this situation, we are in business, because you see, we know everything there is to know about the maximum of the GSF. In particular, we know that it behaves like a log S times an appropriate constant. And if beta is smaller than the critical beta, there's a chance that something here will work. And indeed, the bound, when you do it, when you use that beta is smaller than the critical beta, which translates to b equal 1 in our setup, you need slightly more than the usual. So the usual result is you forget about t. Right? The usual GFF result, you look at t, which is epsilon, essentially, and you put here log of 1 over epsilon, and you definitely show that this quantity is actually very negative. It has a log-log correction. And here I allow you to drop in a rho that is strictly positive. So you have room, okay? But here you need slightly more, because this phi t is a process in t. So you need some continuity argument. It's very easy from standard bounds to work on a lattice of t's, right? Just by Borel-Cantelli or something like that, by simple union bounds, nothing fancy. And then between this lattice of points, you need to do some continuity arguments, but we're dealing with Gaussian fields. So we know everything there is to know about those, and this works. So basically what you show that this object is bounded by some random variable m of order 1, doesn't matter what it is, and then you plug it back in. This means that the object here blows up with s as s goes to 0, but in an integrable way. Everything works in a way that it is integrable, and therefore this gives you the control. And the control is uniform on x, because the right-hand side did not depend on x. Okay? So you got a full control on the infinity norm of the difference field. And if you want continuity, you do the same, except you write the differences in the expression that I wrote. Oops, sorry. In the expression that I wrote before, where is it? Here, in this expression, of course, you take phi t of x and phi t of y, and then you will have here the matrix C dot. Here, this C dot. There will be difference of C dot of x minus C dot of y, and you gain some power of x minus y. So that's how you get.
So you lose a bit of the positivity that way, right? So, but you just do bounds.
What do you mean the positive?
Well, if you do a difference, well, now you look at the drift term at 2 different times, right? So you lose positivity.
Not at 2 different times. At the same time,
Yes,
2 different x. You're talking about the regularity. What I talk about. You look at
You
x
still
and
have
y.
a difference, right? So you don't have positivity.
Yeah, so you have a differential equation.
Right.
So you have a Gromwall type argument. It says that if you control well the difference point-wise, and you Gromwall it, and you get a bound on the integral. Okay? Good. Okay. The control of the maximum, I already answered that. So how do you get from the coupling to the maximum? Of course, the fact that the maximum is bounded by this difference, that's obvious, right? Once I prove the maximum difference, but if you want to actually get the law, you use the fact that this equation converges, and therefore the small scales of the field do not affect it. So you could truncate this extra change, that's it. Okay. Questions so far?
So we did not want regularity, then the difference being positive is just FAG, right? The two fields that the difference, every can come.
So if you only wanted upper bound on the maximum, that would be. But of course, here we are dealing with Okay, so I went way too fast.
So what's the story for the minimum?
Sorry?
So what's the story for the minimum here?
Good question. Yeah, good. Well, no, we have a bound on the infinity norm. Same. Sorry. We have a bound on the infinity norm. We know the difference is positive, but it's also bounded above in absolute value.
Yes,
So
but
it's-
do you get the same like a Gumbel plus?
Yeah, because you move to the minimum of the GFF plus perturbation. The derivative martingale is still perturbed by something that depends on the coarse field. So it's exactly the same story.
The positivity of the field is not, of the difference is not used to derive the scaling limit, it's just a fact that,
No, but it's used to get a bound on the infinity norm.
that's true, but once you have this bound, then you have
Yes.
the limit for the
Yes. The maximum, the minimum, the joint, whatever you want. That's absolutely true. Okay, so where does all this story come from? So for me it was a pleasure to learn it, and since Michael came to be a postdoc, he could teach me. But really, in the context of handling maxima, etc., these are the important works. So the work of Schmidt and Hofstteter, who dealt with the sine-Gordon field. So the sine-Gordon field is a similar story in the sense that the field itself, the V0, is a bounded pointwise function of the field, right? You go in the sine of phi and you integrate the sine of phi and you renormalize. So locally it's bounded, but you multiply it by something that blows up. Here you multiplied it by something that goes to 0. Essentially, you have to make sure, you always in this business make sure that the expectation is 1. Since it's a sine, it's a complex, it's like integrating, finding the characteristic function of a Gaussian. So it's going to 0, so you blow it up by a power of epsilon. So it's, the difficulties are in slightly different places. Anyway, so that was there. It was also used for the phi2 polynomial in the work of Barashko, and Hofstteter. Of course, this PDEs related to sine-Gordon, etc., have a longer history tied with both with regularity structure and other works on that. So I gave a few references. I'm sure there are more. In particular, I'm sure I should have put here Gubinelli, etc. I just have not located the reference. I emphasize that the focus is slightly different in these works. So the focus is not to couple the two fields in the way that you get a bounded difference, but rather to get a well-posedness. The whole question of pointwise bound never appears in those works. You might be able to show it, but it's not there explicitly. Now, I should say something that is puzzling me. So, now it's a little bit of philosophical rambling. Something that puzzles me. There are similar results on extremes that come from gradient models. I believe we may hear about it later today, but in any case, there are many works that deal with gradient models, both discrete and continuous, where you get results on extremes. In particular, in the context of Ginzburg-Landau, this goes back to Jason Miller's coupling, which coupled the Ginzburg-Landau field in a smart way to a GFF. And then this was pushed from this basic idea of coupling to, law of large numbers by Bellius and Wu, law of large numbers by Bellius and Wu, and to results, tightness results by Schweiger, Wu, and myself. The idea of coupling to Gauss is natural, but it's a very different coupling in these works. coupling in this works essentially is not a perfect coupling, and it introduces some error terms that we really don't control, and that are not small. I mean, they are bounded somehow, they don't affect the maximum, but they are definitely not globally small. So the relation between these two ideas of coupling is puzzling. To me, I don't know. I don't have an explicit mathematical statement that would allow you to go from couplings as used in gradient models to these kind of things. I should say also that gradient models, and also models that come from Coulomb gases and from random matrices, they fall in a sense into this gradient model picture. So, okay.
Just one question. For the Sine-Gordon model, the coupling, it's...
For which?
The Sine-Gordon field state. It's below the...
Sine-Gordon, yes.
It's below the first threshold.
Yes. Yes.
So, but perhaps it's not relevant to couple to a Gaussian field above.
You're right. You're right.
So you need to be close to the Gaussian from scratch.
That is true. Here you are always, and for the whole domain you are always. That is definitely. Okay. Okay, so now some words about generalizations. I see you will not get a second talk. I think, so this is a Liouville model. We had a lot going on in our favor here. So we had FKG, we had positivity, we had a lot that we could use. It would be interesting to replace it by the Sinch model, where instead of looking at the integral of E to the field, you look at the cosh. Okay, it's called the Sinch model, but it's really cosh. The reason for Sinch is historical. So you look at E to the field plus E to the minus the field. Okay, in that case, we don't have this sign control to start with. We don't know that the difference is positive. And in fact, I'll come back to that in just a moment. In fact, qualitatively, the behavior of the field under, say, a conditioning of a large mass. So by mass, I really mean, so here the mass was integral of E to the, no, I didn't, no, don't shut off. Can you see what I'm writing here? No? Okay, so, yeah, I thought of using shortcuts, but it was not a good idea. Are you manually pulling it up? Or?
Yes.
Okay, good. So by mass here we had e to the phi with maybe square root beta, and in the cosh it will be e to the square root beta phi plus e to the minus square root, square root beta phi, and here you will have square root beta. And if you, for example, condition on this mass being not large, which is in a sense what this exponential tilting is doing, that, so for example, if you take lambda large in the context of the model I discussed, the behavior of these two fields is very different. This field, in order to make the mass small, what you do is you make the first few levels, or an appropriate number of levels, and we will hear about it later today, negative. This doesn't work here. So this is not the right strategy here. So qualitatively, these two things should look different, but I expect not in what I discussed here, but rather in the discussion what happens when m goes to infinity. Because m goes to infinity has to do with weighting the course. I'll come back to that in a second. Okay. Now something should happen. Maybe being prudent was a good idea. Not using, yeah, okay. In Germany, everything works. As I said, it would be interesting to replace the Liouville model by the Sinch. We don't have definitive sign in the difference field. We believe it will work, but it requires a different argument, and I'm not ready to talk about it. Another model that would be of interest is the zero-mode Liouville. So the zero-mode Liouville, you should think of it as a Liouville with total integral equal to 0. In this case, you cannot make everybody negative in the top, in the coarse field, because the integral would not, that would
You're
destroy.
talking about the integral of the field?
Yes. Or the sum. Yeah, integrals are sums. But on a technical level, you also lose the FKG. It's not a positively correlated. This is probably not a disaster, but at the moment, we don't have results for that.
Now, M is positive or 0?
Sorry?
M positive or
M is always positive. M is always positive. Well, M is coming in one of the next bullet. Another question that makes sense relates to infinite volume, which is related to the question of M. There is some work about that. There is an analysis for the hierarchical version of the zero-mode Liouville that Michael and I did, which shows that you can not only define an infinite volume, but in fact you get a field which has a short range, not a short range, but which has decay of correlation, even uniform in M. You take M to 0, and you still get a field, so you have an infinite volume limit with nice decay of correlation. We cannot show it for the Sinch. And I think that in our setup here, it would be very interesting to study the properties of the difference field as M goes to 0, because for sure it will increase the difference field. The estimates we have are definitely not uniform in M. So I think that morally these questions are all connected. And finally, in the hierarchical model, if you take the Liouville as we took here, not the Liouville, not the zero-mode Liouville, but the true Liouville, then the infinite volume limit, or what happens when you take big boxes, is closely related to a question of entropic repulsion for branching random walk, and this we will hear today. I think we will hear in the talk of Ofer. Okay, so that's the second talk, but I'm not going to. Thank you.